Okay, so here's class 16, and I'm just going to go through some of the stuff that we did in class and then do some of the comparison to stuff between Excel and SolidWorks. All right, so what I wanted to find by hand was to find the velocity of point P here. I had used the same example, modified it here. I modified it a little bit more. Now we're going to use 75 degrees instead of 40 degrees. I made a video previously where we modified a position analysis and turned it into a velocity analysis with a point here on the end. So the first part of this is we want to find the velocity of this point P when we're at that 75 degrees and 25 radians per second as our crank velocity. And then we want to use Excel, MATLAB, and SolidWorks to compare. So from position analysis, we get this 18.25 degrees for theta 3. And we also get what theta 4 is, but we're not going to need it. And then we also do a velocity analysis just as we previously did. And we find that theta 3 is going to be 0.4842 radians per second. And we also find omega 4. So I said, omega 3 and omega 4. So they're both going this direction, by the way. So that's omega 3, and this is omega 4. But when we're not actually going to need omega 4. And we find the velocity of point A right here. We find it in the usual manner. And we get this value right here. We don't need velocity of B and velocity of B with respect to A, because all we're looking for is P right here. So knowing what A is and knowing what the angular velocity are, we'll be able to figure out what P is. So because we're going to be able to say the velocity of P is going to be the velocity of A plus the velocity of P with respect to A. And so we want to find the velocity of P with respect to A. We could do that in a similar manner to what's shown up above. And that is AP as the magnitude of this times omega 3, because this whole thing right here is one piece right here, so it is traveling at omega 3 times J times e to the J, and now the angle of this piece right here is going to be theta 3 plus del, right? Because this is del right here and this is theta 3, so that's the angle. And so we could put the numbers in, and by the way, that theta 3 plus del is going to be 18.25 from our position analysis right here, plus our 15, and that's 33.25 degrees. So AP, we know that's going to be 150 millimeters, and omega 3 we got from our velocity analysis, 0.4842. And then we put the Euler identity multiplied by J, actually, so it's minus sign 33.25 plus J times the cosine 33.2525. And we end up with negative 39.82 plus J of 60.74 millimeters per second. And so that's going to be VP with respect to A. If we want VP, take that VA, add the VP with respect to A to it. So we end up with what we have up here, negative 965.9 plus negative 39.82 plus J is going to be 258.8 plus 60.74. And what we're left with is that we get a 1006 plus J 319.5. These are millimeters per second. So we're going to keep that because we want to compare it to what we get in Excel. So we keep it. All right. And then now we're going to go back to Excel. And I think, yeah, sure enough, I messed that up. So let me delete this guy. And let me go back to where we started. Yeah. I left off in the video where we got the where we did the velocity analysis of the full rotation. We left off right here, so I'm going to create a copy of this so I can modify it as part of this demonstration here, and we pick up where we left off. And I'm going to flip my screen around. So hold on a second. Ta-da! Okay, don't do anything drastic there. Okay, we'll go back. Okay, so now we're flipped back around. This example that I have right here, we have now, instead of 75, we have 100 for this angle. The theta 2 that we're analyzing is at 75, and the del was 15 that we have right here, and we still have this. So we take a look at this point right here, and that looks a lot. That looks, well, it should be the same thing because I made the figure off of the thing. But we come back and we take a look at 75 right here. So let's take a look at what our results are, and we get 1004 and 318.4. So if we were going to do the comparison, which is the all-important thing, 318. So let me. I'll just copy these and put them. Let's see. I like to paste as a picture when I'm doing this kind of thing. Paste as a picture. We could take a look at those and make a comparison between the things. We get. Nope, I copied the wrong thing. Sure enough, silly. Calls himself silly. So paste and boom, and so now we have something we can compare, right? So if we look at this right here, and I do the quick calculation of that, that's like 0.2% difference. That's pretty good. And then this over here, I think I recall this being like 0.3%. So that's like the important part where we're doing the compare, and we're saying that we're off by that amount. And sure enough, it's probably because of the discretization that I've chosen right here, or the increments that I found, these 5-degree increments, which we could surely change to. We could go to 2.5-degree increments right here, right? We're going to have to scroll down to get to 75 is right here, and we could check it out. They're getting better, right? Right here, we could take a look, and we say, putting them side by side onto here. They're looking better. Right? Nope. That looks better. What would happen then? We go to what if? We go to 1.25. So make it even half again. And then for our 75, where did we go? Oh, we got to go down a little bit further. For 75 right here, look how close we get. So that's not so bad with the method in which we got the, that's like, it's like spot on. All right, because I just left this as at 1006. I didn't give any more sig figs, so it'd be kind of interesting if I had kept my sig figs going right here to see what I would have gotten. Now I want to do this. I want to compare these results right here. By the way, this is still a graph. Let me go back to 5-degree increments right here. Okay. So this is where I messed up in the next video here. Is when I went to the SolidWorks, I started to argue with myself about what my increments were going to be. So I'll try not to do that, or I'll pause the video here. Okay, so the thing that we want to do when we get to the SolidWorks is to try to make it as close as possible to the results, or the results that we get from the motion study to be as close as possible to what we're measuring in Excel. So I create a new motion study here. In this model that I've made, where I've made the coupler with the pointy on the end, with the geometry that we've said, I've also put a constraint or a mate onto this to get the crank to start in the horizontal position, because that's the way that we have it in our Excel. So I made that mate right here, but inside the dialog box for the motion, I can go ahead and suppress that mate. Well, what that'll do though is that it put it exactly in the right spot, but now it's released it. I want to change this motion to a motion analysis right here, and I want to apply a motor to my crank. And that motor will be have to be driven at in terms of RPM. So I need to calculate what that's going to be. I'll go down here and I'll just use a blank slide to calculate some things. And so if I have that in radians per second, so I have 25 radians per second. And I'm writing on a screen like far away from the thing. I have to divide by 2 pi, so that's going to be radians per rev, and then multiply by 60 seconds per minute, and that's going to give me an RPM of 238.7. So that's what I'm going to place inside here. So inside this dialog box, 238.7. It's going the correct direction right here. I think everything's good. But the thing is, this is going to go for 5 seconds. I only want to go 3 rotations. Anything more than that's unnecessary. So I got to figure out how much time 3 rotations is going to take. So from that, we'll be fine. We could say that, we could go back up above here and well, just say that we can get 3 rotations. It's going to be divided by 25 radians per second, but divide that by 2 pi radians per rev, right? And what that's going to tell us is what we end up with. We'll get time as part of that right here, and what we end up with is 0.7540 seconds. So coming back into here, what we want to do is we'll grab that and make it smaller. So I'll scroll back up to the top. It's this key thing we want to try to get rid of. By the way, I need to disable this key back play thing. I hate that thing. It messes you up. Trust me. So I will grab this little black thing here and I'll slide it over to close to where I think it needs to be. It's somewhere like right in there. That's probably 0.75. I could get a little closer though, and I could make it right to there. So you'll see I hover over there, and it's going to be 0.755 seconds is the length of this. And I did a little bit of numbers. I think that's about as close as I'm going to get. Now, if I were to run it right now, I'm going to get some kind of bad answers, right? So I could go ahead and run this thing, and I'll do the playback speed slow right in here. I'll just go ahead and put in these values right here. I'll put in the things that we want to look at, the results. So here's the trace right here. I put in the once again, let me see, I'll back up. I went to this plot, results and plots right in there, clicked on that, and I want to choose the displacement, the trace path, and there's nothing there in the third spot, but we'll go to him, and you can see that's no good right there at all. And then we could do this again, the results, and let's take a look at the velocity. Linear velocity, and now in this third one is pulled down, we go in the X component right here, and we're going to pick that same spot right up there. Boom. I think he picked him. Nope, we didn't pick him. I'm going to get that vertex right there. You're going to hover over there. I'm trying not to, I guess I'll zoom in. Come on. I'm hovering right over it. There you go. Alright, so I guess I got to turn the thing over. Alright, so it let me get the vertex there. And anything else I want to hear? Yeah, we're going to create a new plot this time for this. Oh, by the way, I think we'll go back and stick that in later. Okay. We create a plot, and that's pretty poor right here. We could also, while we're here, let's add in another plot, and I want to do the velocity. But this time, yeah, linear velocity. But this time, I want it to be the y component, and I pull him. Okay, once again, he doesn't like me. I'll zoom in on you. Vertex. And let's get back here. Oh, come on. I hate it when it does that. I think is it Shift where this happens? No, it's going to be Alt. Nope, that's not that guy. Makes him turn over there. Oh, man, I hate this thing. Well, nope, that turns it. Shift it. No, Control. There you go. There it is. All right. That was a waste. Anyway, I want to add this to the existing plot right here. And it's going to be plot 4, I guess is what, yeah, that one called right there. And hopefully it'll be the correct thing. You know, this messes me up. Somehow it's got this value is to be way too small. I fixed this not long ago and got it to work out on this plot 4. Something is amiss with this guy. Why, oh why? What did I do to deserve this? We want the y component. Linear velocity. Okay, now it worked out. I don't know why that didn't work out, but you could see that the range. You might not have noticed, but the range over here was like it had like 0.2, but now it's got the same point. By the way, I want to take a look at these, make sure that they're the same thing if they're going to be plotted on top of each other. So I happen to know that negative 1500 was the lowest, and 3000 was the maximum, and 500 is good for right here. And then down here, we could use 100. Doesn't matter. Well, what I'm doing this for, not 1,000, but 100, is so that I can have these be apples and apples, so we can compare them next to each other. This will only matter for this display right here, but I figured. I think I had mentioned something during one of the classes about not liking this, the controls of this. So, but I figured show you, like, if you wanted to use these graphs, what you would do. And make it 100 as the increments. I don't know why they don't make these default to the same things. But now the scales are the same over here so that we can compare. But what's really wrong here is that it doesn't have enough discretization. So what we want to do is go into the controls here and pick out the number of frames. You can see there's only 25 frames per second, and we're not even lasting a full second. So that's the reason why this is only broken down into 25 parts. So let's calculate how many parts that we need. Now, unfortunately, this doesn't work out to be a nice even number. So what you do is we could say that we have 3 rotations, and we're breaking them down into 5-degree increments. So we're taking 360 and dividing it by 5 degrees. So that's 360 degrees by 5 degrees. That ends up being 72 steps per revolution, and we have that ends up being like 216, the answer to this right here. But we want to do that, so that's going to be for number of steps for those 3 rotations. But now we're doing them in 0.7450 seconds. So what we're going to end up with is, when we divide that out, is 286.5, and it sure would have been nice if that was an even number or a whole number right there. I think what I chose is 286. So what's going to happen? Well, the results are going to be that we're not going to have the same increments. We'll get pretty close, but we're not going to have the same increments as in SolidWorks as we will in Excel. So I'll use the 286 right here and say OK, and now I'll calculate that. We can see how much smoother that's going to be. Yeah, take a look how smooth that is. And what we could do now is we can export this to a spreadsheet by right-clicking on that plot down below that's under results. And we don't really care about this, but we do care about these 2 columns right here. So, well, I'll select all these and then put them into my other Excel. So I'm going to Control C these over here, and in my other Excel I'm creating right there. I have a couple things in the way. I'm not sure if I start moving this, if it will remove the data that I just calculated there from my clipboard. But I'm going to stick it right here and hit Control V, and it looks like it came in. So let's say that we want the column widths to be adjusted, and we start taking a look at a comparison here. We can, so you could see, like, let's say right at this time right here, you see that the time, yeah, it's already shifted down. In fact, actually what I needed to do was go move all of this stuff one cell up. So I'll do, because that's where 0 is. So let me delete and go 1 cell up. All right. So I should get rid of that fill. Oh, I didn't mean to do that. Oh, sorry. Okay. Delete that and go 1 cell up. All right. So now you see we got pretty close to being right there at this time. Right. So this is our increment right here, and we can't quite tell. Let's see. Let's just make a comparison. Let's see how far apart they are. We'll say equals, and we'll take that and just divide by this, and just see what they are as a percentage. And you can see they're close, right? But they're about like at this point. They're going to cumulatively get worse as you go down, but they're like at 0.135% difference between them right now, right? Just as a ratio of the 2 things. So that's just a guesstimate of them. Actually, if we were going to do this, we probably say, let's call that one's the right. Let's arbitrarily say that one's the right one. At least that's the way I think of it. It's like which one's the right one is the one, and that's the one that we divide by, right? Or the one that we're using as a means of comparison. And yeah, you see, so it's 0.135% difference at this point right here. But we could take a look and see what the results are right here. Those are not too shabby, right? That's the 1000.6, and there's the 318.9. Very close to what we got by hand, right in there. So maybe we want to go ahead and say that's the one that we want to compare, or like let's actually let's get these formatted to the same thing, and you could see as a means of comparison that we had down here. Here is going to be what our Excel is. Pretty darn good of our hand calculations, Excel, and then there is the results of our SolidWorks. And by the way, that SolidWorks result right there, we could also grab a hold of this and copy and paste it. I think I did during class. And then lastly, for the MATLAB, let me take a check, see what the time is on this. It's already at 26. So if you've made it this far, you probably don't have to go any further because I haven't given anybody but only the 501 people the MATLAB. So let's take a look. Let's take a look at the MATLAB. All right. So if I were to start out with what I posted as the MATLAB assignment for those people who are doing that. Let's see what here. Oh, I see what I do. I'm on the other computer right now. I go to University of Hartford and 401. And is it under assignments or is it under MATLAB? I think it's probably under MATLAB, where I had written that text file. Yeah. So this is what I loaded up onto Blackboard for you to do. And I'll probably have to cheat and look back, but I go Control-C because it's just a text file right now. And I open up in a blank M file, and now we have it in MATLAB. And if we wanted to, we could save this, maybe save as, example. Let's see. I'll just say 4.3.20. I just got to give it. Actually, it might not like that dash. I think it actually doesn't like that dash. I'm sorry. I seem to recall M codes are not happy with dashes. They want underscores. All right, so I could just hit run. It'll clear out my thing here. And do I have a plot? Well, I didn't put a plot in here. Okay. So, but what I have done is I have figured out this position right here. And all right, so the 3D printer there, he finished up. And we want to plot this probably. Just to check what this. Let's see. Did I work on this? Did I do? I don't know if I've done a MATLAB problem yet, as part of a video. I should go back and check. Anyway, so what I want you to do is to include notes with a brief explanation, with brief explanations on each step of the existing code of what each step does. That's not really written very well. So fix the grammar of this. That's your first task. And then include notes where you modify or add code with explanations as well. And everywhere you see a parentheses there, you need to add a comment. So I'm trying to make it clear that I want you to really be documenting this stuff well. What am I doing by making zeros that are the length of this plus 1? It doesn't need to be long, but just try to explain what's the purpose of this. This one you could answer that you want to create the string one cell longer, or something like that. I mean, it just doesn't need to be very long. But hopefully you know why you need to create the zeros. Well, one thing that you could do if you don't know is what we could do is we could comment this out right here, and then as you run the thing, it might tell you, or sometimes it'll actually, let's see. Did it? Was there any effect on it right here? A lot of times it'll tell you that it wants you to do that. That it wants you to make create a string. That's because it was it appears this thing is getting longer every time. That's what it does down here. But I don't know. It seems to me that yeah, right here. Let's see, down here it goes. The variable th3. There you go. There's the reason why. Appears to change size on every loop. With script, consider pre-allocating for speed. So you could use the word that we're pre-allocating the variable to increase the speed. Something like that. Now, maybe the speed's kind of dangerous because that sounds like we're doing dynamics, and it sounds like that's the speed. It's a processing speed. So anyway, we take this one right here, and yeah, okay. So these are like what are those equations right here? And we want to take the cosine of this divided by that right there. I'm trying to remember what this is right here. Oh, I think this is like a good place to start. Like this is like an estimate of where the thing might be. So you're kind of trying to get it into like sort of like the correct range so that you have a good place to guess. I'm not actually sure. Let's see what would happen if we were to comment this out right here. Let's see. We'll uncomment this. I won't spend much more time doing these things. We'll just take a look and see what this does. And boom, boom, boom. It doesn't like it because I think it's starting out with bad values. So what you're doing when you're coming up to here is you're taking you're replacing that first row, or the first I guess column actually, because I think these are horizontal arrays. When you're up here, you're replacing that first zero with something. It's helping you to get a guess. And I'm trying to figure out what I used as the rationale when I went to go make this on that first guess. I think I might have, actually, I think I might have made it what happened here. Yes. Okay. So what this is the law of cosines, I believe, or getting close to it. Yes. I believe so. Yes. Okay. And what I did is I figured out what the angles were. These are the correct angles for when the crank is in the horizontal position, right? So when the crank is equal to, when theta 2 is equal to 0, here are the angles that theta 3 and theta 4 actually are. So I have a good place to start my calculations. So what you see here in this is that we take n is equal to 2 times the length plus 1. So that's the reason why, one of the reasons why I went to plus 1 up here, is that I wanted to start someplace. So I take my first estimate and I actually make it at cell 1. And then I take this f. Okay, so f is now going to be, well, we just start out with a value. That's just something to start with. And then they take the norm. And what you should do is you should look up the norm right here. You can go help on norm, or open, or you can just go open norm right here. Now you don't want to open norm. Sorry, that help on norm. You want to help on norm and understand what a norm does, right? Is we find, I'm trying to actually remember what it returns the Euclidean normal vector of this, And I think that usually means for a 2 by 2 returns the generalized V prime norm. I'm trying to remember what the norm is. I think the maximum, if P is equal to 2, is approximately equal, this is the equivalent of the norm of X. Yeah, I'm trying to remember what a norm is. Right here, 1, 2, 3, the norm of a vector is 6. Anyway, what we're trying to find something that's that makes it small. I think that's what they mean right here. Right? Yeah, we're trying to find. I'm trying to remember what a norm is. Damn. I'm sorry. I'm going to cut this out. But anyway, you take the norm of f, and we're going to use this as a criterion to see where it gets small. And then we take what this is right here is our x and our y of this is our x and our y equations right here. And then we take here is the I believe this is the Jacobian. Yep, the Jacobian. And here is the other side of the thing. And then here is this value of x, and we want to get it to go small. And then I think we plug this this estimate back in there. Right, and we're able to come back the other side and get what the next one's going to be. Right, we populate what the man. This is terrible. I'm going to go back and cut this out. Restart now. Okay, so this is your assignment for the 501 students. I want you to go through and just go step by step and explain what's taking place. So, for instance, you might explain why you have these zeros here, and the explanation you might find out that if you try to run it without, you will get a solution to it. But if you look at this error down there, it says that note that the variable is changing size in every loop iteration. Consider pre-allocating speed. So you'll say what you do here is you're pre-allocating for processor speed. And so we want to try to get rid of that. Here we go, uncommon. And so forth right here. This right here, the purpose of it is like this calculates theta 3 when theta 2 is equal to 0. Same thing here. Calculate theta 4 when theta 2 is equal to 0. So this is the initial step. And then we might say, well, this is a loop that goes from here. And the reason why I'm making you do the comments is I really want you to think the thing through. This is going to be the challenging part right here, is I want you to explain what's taking place right in here from the previous stuff that we had done. So you're going to have to go back and take a look at that numerical processing as we go through and try to figure out the position analysis using the Newton-Raphson iteration right here, so the Newton-Raphson solution. So make sure you go through there and think about what each of these things are going to be. Now we want to modify this for our velocity. Okay, and the simple way to approach this. Well, first off, I'm not sure if the original one that I had right here. Let me go back and tell you what these are for. Remember, we made this thing one thing longer than we needed to, and that first step that we had right here was an unnecessary one, right? So because we and we actually might make actually this one we actually might want to make the end one. I might actually want to replace this and say end. We could get rid of the last one. I might think about that. In fact, actually, let me double check and see. Let me run this without the thing, and then take a look. Okay, so theta. Let's see. Did I get rid of this thing? Let's see. Let me. How come theta 2? Oh, I see. Okay. So, like, if you take a look at theta 3 right here, yeah, you see that the first cell is the same as the second cell. So, in terms of like the way this thing was done, so yeah, we do need to have that thing. We do want to get rid of the first cell. So that was correct. A lot of times it's the last one we want to get rid of. So what I've done here is I just went ahead and found the thing that we had just done in terms of the position analysis to get the motion of the coupler. And I almost want to make this, I don't know why CCX. I might want to go like PX, I think. I almost want PX and PY instead. That would be a lot more, make a lot more sense. So I'm going to get rid of that. Yeah, PX. I don't know why we had CC. And now I want to get the velocity of these things. And let me go here, and I'm just going to steal what I've written before. So all we need to do to find the velocity is, well, first we need to create some time. So I need these things right here, right? And so let's explain what they are. Are they already in this code right up here? No, they're. Oh no, they. One of them is. Okay, so I accidentally left it into the thing that I uploaded for you, right? So omega was already in there. Check crank to the crank input there. But I also need to establish what time is right here. So with that speed right there, I'm able to do the same thing I do in Excel here, but I'm able to instead create time string or something like that, a string of time, an array, of time increments. And I'm putting it up here just because it makes more sense to be at the very top of the thing, but won't need it till we get down here. And we're going to use the command, the diff command, I believe. Yes. So this is a typical thing that we would do. We come in here and we say that we want to take the numerical differentiation here of, in this case, we want to make P and P, right, of the thing, right? So, and then write that next to it, right? Put what this is into here. So numerical differentiation of position of P. Something like that in X direction. This type of thing will really help you later on, because I can't tell you how many times I've written a MATLAB code and then had to come back to it and try to use it again and not know what the hell it was that I was doing and have to relearn all the stuff. Especially if you're like me, if you have to do lots of different tasks and you're not using MATLAB all the time, it's really easy to forget what all the things do. So anyway, that will give us the velocity, and it sure would be nice to be able to plot those, right? So we'll take a figure. Oh, and by the way, before we plot them, we need to make them all the same. Okay, so here's one that I haven't done yet right here. I want to, interesting thing that I did down below. Oh, I see what I did. Okay. Let's say that I want to plot. I could plot this right here if I wanted to. Let me plot, and then I changed these, so I don't know why I did that. Plot PX versus PY, and I make a new figure. I call out to make a new figure. And there you go. There's the figure thing that we have. And then I want you to come in and I also want you to plot the, yeah. We'll see what happens here. Let's go to just plot these by time, right? So we want to plot them on top of each other. If we go to plot these right now, the way that we have them right here, we get they're not the same length. Also, oh yeah, by the way, I haven't run everything yet. So let me just run these. Yeah, okay. So and now we want to if we wanted to try to plot the velocity versus time, we're going to say that they're not the same length, because if you take a look, time is 217, and then but the velocities are 216. So that's our reason for cutting off the end of the time. So we'll put them right in here, and so before we go and try to plot them out right here, and we needed time to be one longer than when we did the differentiation. Is that true? No, I guess. Well, no. That was the reason why. I'm sorry. That's the reason why time is one longer when you do the differentiation of the position with respect to time. It just can't do the last one, just like in Excel. So we run this right here, and now we're able to plot one versus the other one right here. And now here's a reason why you might not be able to do this successfully in the online version of this, and that's because I'm not sure that you can export things, but we want to get Excel data, or we want to get something we can open up in Excel. So there's a number of ways to do it. You can look it up online. What I found was the way to go, I think, is use write matrix, and then I want to put them all, do it all at one time, right? So what I've done here is, first off, I want to make my position. I want to use my positions in there too, just out of curiosity. You don't have to do this, so maybe I will skip that part right there. But if you wanted to, I had to make them the same length to try to combine them together. So I'll get rid of that. What I decided to do was to combine time and the velocities and do them as columns, right? So that's another thing I'm doing. So that the little apostrophe next to it, that transposes our horizontal array to our vertical array, and then we add them together with these brackets. And now I'm able to write what these things are. So I put them together like this right here, and it's going to write this, by the way, in the local directory, which I happen to have something. I happen to have already run it, so you already see that it's in there. So it's going to replace that. But I run this right here, and what I'm able to do under my MATLAB, is that true? I think I have, this is going to be under MATLAB and examples. Yes, under examples. And here, and yes, it was, this just got made. So we can open this up right here. And so now what we have inside here, I think this one's old. I don't think this did the thing I wanted it to do. Is that true? Huh. Let me cancel out of this. I don't. It set. I know what happens. We got to be careful here when we're running these. Let's see. What is that one? That's just sheet 2. Let me get rid of him. When we are, it just adds to files, right? So let me delete this, if it'll let me. So it just added to that existing file. So you got to be careful with that. But now we'll just run it again here, and all I need is to run this one and evaluate this selection. And you're going to see here in a second. Okay, see it popped up again. So now we're going to open this up, and you're going to see that it only has the 3 columns that we expect. And then we can go ahead and bring these over and copy and paste. And I made that thing way longer than it needed to be, but see, there's 216 steps as part of that. Although I think the increment might be different from our one before. And let me see here. Let's open up my Excel right here. And I believe this is the right place to put it. Kaboom. And we should keep track of this stuff. So let me, above this one, write SolidWorks. And over here, we'll write MATLAB. And this is time. And this is time. And this is, all of these are the same things, right? No. Oh, these are the same things because I didn't put in, we don't really care about the magnitude there. So let me stick these in here, and maybe we could put that in there just to remind ourselves what it is we're looking at right here. It would be nice to put in, well, I don't, okay, so, oh yeah, because the other guys right here, I think I've actually have like multiple loops. I have more than one loop. I have more than 3 loops, I'm sorry, through there. So we can superimpose these if we'd like, all onto one graph. Let me move this guy out of the way for a while. And this guy was for way too many rotations. So let's get rid of that just to clean things up. And I think it was 1080 was all we needed to go down to. It's like, sure enough, we only needed to go down this far. So we can get rid of all that stuff. And let's see here. Yeah, so that's 3. That should only be 3 rotations, and we can graph all of these. But the thing is, they're going to be so close to each other, we might not be able to see them. So it's good to put a graph into the thing, but it's not necessarily going to be necessary for your report into this, unless you want to zoom in really closely. But what will be useful is to find out things like the difference, the percentage difference between them. And I know this is just way too long of a video here, but let's check this out right here. You know what I did? I think I forgot to put something that I wanted to in the SolidWorks part of this video. Oh man, I wish I could, like, I need to write these things down. Anyway, here's the whole graph. I think we've shown this previously. If we wanted to, we could let me see if this works right here. I'm going to add in. I'll just do the X direction. We add in the X direction of the MATLAB on top of the thing. Maybe I should do the SolidWorks on top of the thing too. I should edit this out. All right, but this is versus time right here. You can see they probably shifted over just ever so slightly, but they should be the same. I think it's just that they're not. We're not at the same angle as the other one. And then we could also do the same thing for the SolidWorks. So let's see what happens here for SolidWorks. Nope, did I accidentally grab? That's supposed to be the. Then we come down to time. And you can see that it's difficult to actually see some of the differences between here. We really need to, when it comes to the lines, to get the line weight down pretty far. And same thing true with the one that we just did a second ago. Yeah, but we should have put that down as MATLAB right in there, by the way. Make this one pretty small, and then I don't know, we got to zoom into some spot really to try to get a better look at the thing. Like we could try to go for the peak right in here, and say go between 0.2 and 0.3, and take a look and kind of see what those are, and maybe even zoom in a little bit closer. And some of the problems that we might not have started exactly. We should have started in the exact same spot. So I'm not quite sure why we've shifted over. It could be because we've numerically solved the thing. It's an interesting aspect. But you can actually see that they're kind of faceted a little bit here. So like we could zoom in some more. Let's go to let's see, I guess I'll go 0.2 35, and let's go 0.24. All right, so that's zoomed in too much. Let's go 0.245. Yeah, maybe we need to also zoom in here to be able to see this better. And so we want to go 2500. And yeah, interesting. Which one is this one right here? Let's see. That's the Excel one right here. Now, one thing we have to be careful of when looking at this is we might have smoothed this one out. Yep, that's some of the issue right here. You got to get rid of that smooth line so you can kind of actually take a look at the difference here. Some of the differences are going to be because of the time increment, right? The time's not going to be identical to each other. So that's an interesting thing. But maybe what we should actually be doing is let's take a look at what the difference in time really is. So we go equals, I don't know. Let's go. We could just take a numerical value. We don't need to take a percentage. How far the thing is off, right? Maybe that's a good thing. We'll take a look at the SolidWorks, and then also take a look at right here equals this minus the MATLAB. Boom. And let's take a look at those. Let's see what those are. All right, so that's not going to tell us a whole lot. Let me make this into scientific notation. We can see that the MATLAB is identical. All right, that's something we probably should have already known, but that the SolidWorks definitely has something, and it's accumulating. It's getting larger because the time steps were different. I believe it is, yeah. Well, it's getting larger, but it's getting more negative. So yeah, so you can see that it's increasing as we go through. But still, it's just a small difference. But it does shift things. It is going to shift things over. So it's going to get worse and worse as you look through right here. It probably is that true? No. It's not going to be not here, but in terms of the RS rows. And right in here, yeah. And then we could also so let's I'm only going to look in the X direction. Let's take it and let's pretend the one from by hand, I guess, is going to be the thing we care about, right? The one that we consider correct. We'll say sorry, I should have gone right here and go VX. Well, we don't want to do that one. We're next row down. Sorry. We'll say VX minus the SolidWorks divided by this right here. Boom. And let's do the same thing over here, but this time we'll put both of those cells right there. Okay, so now that's going to be MATLAB. So these should be really the percentage difference. And this first one right here is pretty substantial. That's kind of interesting. It's 133%. So I must have done something wrong. Oh, I know. Because it didn't do that, it's supposed to be over this one. There you go. Okay. Still is 11%. Jeez. Huh. That's interesting. What is going on right here? Why is this one so much worse than here? Well, oh, you know what I did wrong? No. What's going on right here? Why is this one -8? I guess because they're pretty small numbers. I don't know. MATLAB versus, so it's negative. What the hell happened here? What's going on? Why is that one so much different? What is happening in MATLAB where it is not liking periodically? Does that show up somewhere in here? When you go to I don't see it anywhere. I guess it's like somewhere in the small values, but it does look like it's periodic. It's an interesting thing. What is taking place every now and then? I go right to there, and it is significantly different. I think it's somewhat because of the shift. That's what I think. I think because of the shift, when we get the Vx, when it gets really close to 0, it has been shifted over. So therefore, it's that's what that is. It's unfortunate. It's difficult to compare these things because they don't have the same time step. So that might be the thing, the takeaway that we have here. But I think I've wasted a lot of time, and I'm afraid to even see what this video looks like right now.